Okay, so some of you are having some of you are having a little bit of trouble with accessing the GPU machines and setting up your Jupyter environment. But just go through the process. It's a little bit painful, but once you have set up the Jupyter running on the other side, you only have to execute the tunneling command, the SSH tunneling command, and keep connecting to your server. Okay, and yeah, multiple people. If you want to connect to the same, there are multiple people in a team, you need to add each of your SSH public keys one after the other to that authorized keys file. Okay, if you have some question about this, then post it on the forum. Hopefully somebody can guide you. Okay, no, you can use the same public key. Yes, I mean not the same public key, but you need to use the same private key. Okay, I mean once you have put a public key on the other side, use the same private keys. There's a link which I sent to you guys, right? I mean, which is a GitHub link about how to set up these keys. So there's more information about that. You should explore it. Okay. Okay. So the last point is that there is actually a PyTorch tutorial by I forget the name, Ben Trevet. So there's a GitHub repo which actually goes through not just sentence classification, CNN-based sentence classification. It also looks at some more exotic architectures like RNNs and so on, which we'll see in the later class. Okay, so actually there are many implementations of the architecture that I talked about from 2014, which is actually this first link. Okay. So there are many implementations of this because it was quite effective when people were not sure why would somebody use a CNN for a sentence classification task, but somebody built an architecture and said this is how you use a CNN layer and showed that it performs really well, right? So there are several implementations available online, and so one of the implementations is from this tutorial, and I think the fourth notebook in this tutorial is essentially going through how to use Torch, okay, or PyTorch, and another module called Torch Text. Okay, Torch Text lets you abstract away a lot of the nitty-gritty details of dealing with textual data. For example, in this case, we can actually get the data set, which is the IMDb data directly. Okay, you just a command from datasets class. So the first time you run it, it'll basically download the data set, this data set from the internet, and then there is this step where it's actually downloading a huge file, okay, which is in this case glow.6b.zip. Okay, so we're going to look at what glow is. I mean, we'll not go into the details, but glow is essentially a collection of word embeddings, okay, which essentially means for every word there's a vector. In this case, a 100-dimensional vector in this particular zip file. So for every word in the English language, for a sizable chunk of these words, there's a vector, 100-dimensional vector, and there's a zipped version of this. And this particular notebook downloads that word embeddings, and that's going to be the matrix, initial matrix we saw, right? We saw a matrix which has a dimension of 5 in the slide. So instead of 5, it's going to be a 100-dimensional vector, okay, which are these predetermined vectors, and we'll see how they are constructed, okay. And then it's basically the usual procedure. You should check whether you're actually using the GPU, okay. So just check whether you're actually using the GPU, and sometimes you can actually see how much memory you're consuming, okay. Actually here, example. So this run, so I just ran this a few hours ago, and it's using 3 gigabytes out of the 8 GB memory that it has, the GPU has, okay. Next, I mean, this is basically the description of what we just discussed, so definitely go through this document. Again, this is linked on the lecture, the syllabus page, and the rest of the procedure is essentially defining, what is the CNN module in gory details, okay. What is the forward step, and basically train. For example, here they're looking at they explicitly define what the accuracy, what the loss function is. Okay, and then the training step is, use the optimizer, appropriate optimizer, and do a step in each round for each batch, and then log the information. So I think here they're getting an accuracy of 86%, but this is not the same data set that we just discussed. So the MR data set where there was 81% accuracy is different from this particular data set, which is IMDb data set. And here is some example of like the sentiment of this film is terrible. Sentiment is close to 0, essentially a negative sentiment. And if this film is great, it's a very highly positive sentiment. Okay, so the purpose is not just to, of course, for the first time, definitely run through what's, just ensure that the whole thing is working, but also try to understand what's happening in each function and each step. Okay, so okay. So that comes to the then we come to the idea of embeddings. Okay, I have actually used the word embedding when I was talking about transfer learning. So think of that feature extraction type of transfer learning, where I was saying that the final 1000-dimensional vector or 512-dimensional vector, I was calling that as an embedding of the image. So the image is whatever dimensions I got through this feature extraction process. I got a vector, right? So I was calling that an embedding of that image. Okay. So I've used that word embedding. Embedding just means a representation. Okay, and we'll get to what why what is an embedding. Before that, let's understand why bag of words representation is lacking in. Okay, so what the bag of words or TF-IDF type of feature vectors are lacking is that they are not capturing the semantic similarity between words. Semantic similarity means a word like dog and cat. Those two words probably are semantically closer to each other than something like a book or a house. Okay, so that's the idea, and you want to somehow capture the semantic relationship, and there are models which capture this relationship, and they're generally called vector space models. Okay, which is a quite generic term. Vector space models means somehow use vectors. Basically, and they rely on trying to capitalize on this hypothesis, which is called the distributional hypothesis, which is that words that appear in same contexts share the same semantic meaning. Okay, so if you can think of synonyms, right, you can replace pretty much the word as is, and the semantic meaning of the sentence remains the same. Okay, that's essentially the definition of I guess a synonym. So in a similar vein, words that appear in similar contexts hopefully share similar semantic meaning. Okay, if cats and dogs appear in sentences where they're talking about pets and pet food and stuff like that, then they are probably similar. Okay, so there are two types of approaches, and as a warm-up, I'll just go through the first approach, which is count-based. Okay, and then rest of the part will be actually how do you get Word2Vec, and that's the prediction-based approach. Okay, so what are these approaches? These approaches are trying to capture semantic relationship between words in the sense of the words should be represented as eventually as vectors, because these are vector space family of models. So I want to get vectors for words, but those vectors capture semantic meanings of the words. Okay, and yeah, so let me tell you a very simple way to capture semantic meaning, which is, let's say you have a corpus. Corpus just means a collection of sentences, documents, text. Okay, you already got in the text, strings essentially. So what you do is the following. So let's say you have a vocabulary. Vocabulary means lexicographically ordered sequence of words. Just think of the dictionary words. Okay. I'm describing the first approach, which is count based. What you do is you construct a matrix. Okay, which is essentially a count matrix, by which I mean that think of a, let's say vocabulary size is 100. Okay, there are only 100 words in this example. Then let me create a matrix which is 100 cross 100. Okay, so it's going to be a matrix of word versus word, and the entry in the matrix is going to represent whether these two words appeared uh, close to each other. I mean, there are different ways to capture this matrix. I mean, different ways to define a matrix between words and words. So we're going to look at two words which appear uh, near each other in the corpus. Okay, so there are different. So this is one way to define this matrix. I mean, there could be other matrices, right? So I'm just saying that if two words are very close to each other in sentences, then put a count of one. Maybe, so think of two words, right? Dog and pet. Okay, maybe they appear close to each other. Let's say hypothetically. Then for the entry corresponding to pet and dog, just increment a count. Okay, from your corpus. Just do that for do this for all words. So what are you capturing? Words that are appearing together, essentially. Okay, right? So increment the count. So this is a count based matrix. So each entry is essentially a count of how many times the word appears, word pair appear together in your corpus. Okay. Then given this matrix, do a PCA operation. Okay. So PCA is essentially many of you know is essentially a way to reduce dimensions, right? So what would PCA give me? It will give me a matrix which is 100 cross whatever dimensions I pick. For example, D. Okay, so for every word it will give me a vector. Okay, which is a d-dimensional vector. Okay, so this is an example of a vector. So now for each word I have a vector, and the vector hopefully captures a semantic meaning of the word. Okay, that's the idea here. Okay, so is the idea clear? So is this a computational procedure? I'm just trying to improve upon bag of words, and we'll see Word2Vec later. But I'm just saying that, okay, given the corpus, just create this matrix where, of course, I have not very rigorously defined how do I increment counts in my cells. Okay, I'm just saying that increment the count as long as the words appear together in within vicinity of each other in a sentence. Okay, that's one way. But the actual right way would be those words should appear in the same sentence. Same type of sentence, if the words appear, then you increment the count. But that's something that's hard to compute, difficult to, I guess, compute. So let's just say two words, you increment the count if they are in the same region, they are nearby words. Okay. And given that, I'll do a PCA, I'll get a small, dimensional reduction. So therefore, I'll get vectors per word. And these vectors are essentially somehow capturing some semantic relationship between the words. Okay, and the way to intuit about this is not in terms of words terminology. Think of this collaborative filtering application. Okay, where you instead of words you have movies. Okay, so yeah, let's think of a movie versus movie matrix, where each cell just represents how many common people watched these two different movies together. Okay, then let's say you have that count matrix. Then if you do a PCA, then movies, the vectors corresponding to movies is 100 cross D, or this d-dimensional vector corresponding to movie 1 and d-dimensional vector corresponding to movie 2 will be similar if the if the movies were watched by if had high numbers in these entries. Okay, it's just an idea that, okay, if they have high numbers, then their inner product is going to be high. If it's the same vector, then the inner product is going to be the highest. Let's say they are all normalized vectors, then that's the idea. So if the numbers are high for two movies, then hopefully they have the same they have the same vector representation, something like that. That's kind of the intuition behind doing this counts and then PCA. Okay, any questions about this part? Okay. So, but okay, that's fine. But we're actually going to do it in a better way, which is prediction-based way of capturing semantic meaning. So, the prediction-based way of creating these vectors for words. Okay, and so for that, I'll kind of formally say what an embedding is. An embedding is a some transformation or some W, which given a word gives me that vector. Okay, gives me a vector. So it's like a function. Think of it as a function. Function call where you give the word as an input, a string as an input, and it will output a vector. Okay, so that's called a word embedding function, right? W, capital W. That's what I use here, and whatever. I mean, the dimension that you decide is arbitrary. You don't have to use the full. I mean, you don't have to. Like here, I've picked the dimension 300, right? If you think of a bag of words representation, if you have a vocabulary size of 50,000, then you'll have to have a 50,000 dimensional vector, where a certain coordinate is going to be 1 if the word is present, for example. Okay, so immediately you've gotten a reduction in the dimensionality, right, of vector representations of words. Okay. Here are some examples, I guess, of if you use university, there's some vector. If you use class, there's some other vector. And now the question is going to be, how do we learn this embedding? So I'm using the representation W, but just think of it as learning this guy over here. Okay, if I know this, then it's a dictionary lookup, right? Given the word, I just look at the that word's corresponding row and just output that vector. So that embedding is nothing but a matrix. Okay, it's just a collection of these row vectors, where each vector is a vector representation of a word. Okay, that's all. Okay, so you don't have to really think about functions here. So the way we're gonna learn an embedding. So this is going to be first we're going to start with a general idea, and then we'll specialize it to Word2Vec. Okay, the general idea is. Okay, the general idea is we want to learn W. Okay, and I just said W is essentially think of it as a matrix. Okay, so it's the number of vocab size times D, where D can be, let's say, 10. Okay, let me use vocab size as let's say vocab size is 10,000 and D is 300, just to be consistent with the D or N I was using. Like N is 300 there in the slides. So let's say I want to pick 300 dimensional vectors for each of my words, and let's say I have 10,000 words. Okay, so I want to somehow learn these guys. Okay, learn the entries in this matrix, right? And the way I'm going to learn these entries is to attach an auxiliary task. Okay, or create an auxiliary task. Okay, I'll just concoct a task where I'll concoct some objective and solve the task, such that as a return I'll get some semantically good entries or semantically relevant vector representations of W as a byproduct. Okay, and the example task is here. So I'm gonna train a network. It doesn't have to be a network. Train a model to classify whether an input sequence of 5 words is valid or not. Okay, so I have a corpus of words. I want to get word representations. So, but I can also look at the corpus and look at all sequence of 5 words, all successive sequence of 5 words, and say, okay, if it's a successive sequence that appeared in my corpus, it's valid. So +1 score. And if I arbitrarily change a word in that sequence, then it's not a valid sequence. Okay, so here's an example. So let's say the word sequences operates the largest medical school. Okay, some arbitrary phrase. Okay, yeah, so you can arbitrarily change a word in that sequence, in that phrase. Let's say instead of largest, I made it consistently. Then that's an invalid sequence. Okay, I arbitrarily change the word, I call it an invalid sequence. Now I have actually a data where I have sequences of words, positive label, valid, sequences of words where things were jumbled, and I have a negative label. Okay, so I have a binary classification task that I concocted, right? Then I can do the following, which is that I have many such words, sequences of words, labels, right? So my learning problem is going to be as follows. This is something I just created, which is if the right sequence of words I want to predict as valid, and for the incorrect sequence of words I want to predict invalid. And how are the sequence of words being passed on to get to the loss value? Okay, to get to the loss. If yeah.
So if you're changing words randomly, so we're changing them from our vocabulary, right?
Yeah.
From a whole set of words.
Yeah.
There could be some other words which make sense in sentence.
Yes.
Right? So
Yes.
how will we know that those valid have been marked? Like
yeah, I mean,
we need to give them also labels, right? That this is a valid sentence.
Yes, yes. So you can ignore it, and probably it's not going to be a big deal. Okay.
But then, like, in the whole set of examples,
yeah, there could be something which will be incorrect.
Example we have.
No, we have many valid examples. So in our corpus, think of let's say our sentence. Our sentence has 100 words. So every sequence of 5 words is a valid version, a valid example. And for every sequence, I can randomly drop a word and put some other word there and call it invalid. So I can create many data set, arbitrary size data set here, right? So if in the case that you're saying that, okay, for a 5 sequence, I somehow randomly put some other word, but it still makes sense, then there is a problem, then I'm saying that don't worry about it.
Like if you change the largest by smallest, it again makes sense.
Yes, it does, yeah. So we are not worried about that, yeah. But if that effect is there, if it's really large, then we have to do something else, yeah. So here, so I was just explaining how we're going to go, what is the forward pass here, okay? So let's start with this W. We said W is a matrix now. So for these sequence of 5 words, we'll look up the entries of my matrix, the 5 entries of the matrix, right? There are 5 rows that correspond to these 5 words. So those 5 vectors I'll pick, and then I'll concatenate those vectors. I haven't shown it here, but think of it as a simple way to concatenate those vectors and just pass it on as a feature for my classification task. Is that fine?
So each box of W is a vector there, or it's a matrix?
So W is that transformation, or like think of a function call. Given the string, I got a vector out. Okay. Dimensional vector. Yeah. So the edge, this edge is essentially a 300 dimensional vector. Yeah. Yeah. Here, if I concatenate it, I can add it, whatever. So it's thing is, I'm concocting this particular experiment, right? So let's assume we concatenate it. Yeah, it's going to be 1500 dimensional vector, and then let's say I'm doing softmax logic regression. Okay, binary classification problem. So these numbers get multiplied with the classifier's weights, and then I get a score, whether it's valid or invalid, whichever score is higher. Based on that, I'll have a binary cross entropy loss, right? So then given the loss, now I'm backpropping. I'll update the classifier's weights, but I'll also update these W entries. Okay. I'll also update the entries of my W matrix. Okay. That's the, I guess, non-trivial part. So it's like what we just did is we had this lookup table or lookup function with W. Given any string, it will spit out a vector. In my classification task, I'm just creating, let's say, these 5 words. I'll create those 5 vectors, generate those 5 vectors, given the current weight entries in the matrix, pass it forward. I'll get a loss value because it's let's say the classifier is just a logistic regression classifier. I can multiply numbers and the usual classification sequence and get the loss, and I backprop to update the weights of the classifier, but I also update the entries of the W matrix. Why not? They all went into the computation. So remember the first class backprop, whatever entries were there, finally if I compute something, I can always compute the gradient with respect to every entry, everything that went into the computation. Yeah. Yeah. Any other questions?
only these valid strings or valid words will come into this each of the W transformation.
No, it could be you. Let's say you arbitrarily replace largest with consistently, which we saw in the previous slide. Then there'll be a W. There'll be a consistently corresponding row vector, and you give that vector as an input now. And for that, that vector. Okay, where is this? Let me just draw it here. So let's say, this is the right let's call it word1, word2, word3, word4, word5. All I'm saying is do the dictionary lookup, you'll get vectors, right? 300 cross 1. Here same thing, same thing, same thing, same thing. Maybe concatenate and then pass it to a simple classifier, like a SVM classifier or multi-class logistic regression classifier or whatever. Now if you drop this word, let's say this was the word largest, and I drop this and put it consistently there will be a different vector here, right? Because the W, these words just are lookup tables, indices of the W matrix. And then if you concat, there will be a part of that concatenated vector which will be different, right, corresponding to this incorrect word. Them together, they should give me an error or invalid. They should maximize the score for the invalid part. Whereas if the word was largest, them together should give me the score for the valid highest. Okay, so that's how I'm trying to capture that these vectors, they're capturing semantic meanings. Okay, because if this sequence of words, they are close to each other, right, then they are appearing in similar contexts. Okay, if they are nearby in sentences, right, then they are literally appearing in similar contexts. Okay, for those sequences I'm calling them valid, so for them I'm raising the score. So their representation should be such that if them together, they are all being updated to they're all getting a gradient updated if they are together, if it's valid. Similarly, if one of the words is invalid, they're all getting gradient updated but towards the opposite direction, because if they co-occur, then it should be invalid. Okay, so that's the thing which is at play here. The sequence, the consecutive sequence, is part where I'm capturing that they are nearby to each other, so they're appearing in similar contexts. Okay, and me randomly knocking off words and putting arbitrary words, they do not appear in similar contexts. For that, I'm ensuring that the weights learned are such that for similar context words, I'm trying to push them towards valid, and non-similar context words, I'm trying to push them towards invalid. Right. The numbers that get filled in this W matrix will capture that aspect. Okay. That's okay. So we saw this. So let's say we did that conceptual task. I created this classification, and let's say I updated my embedding matrix. How good are these? So literally, we'll see Word2Vec in a little bit more detail in a couple of minutes. But there are a couple of such embeddings, such people hallucinated and created some tasks and literally learned these W matrices. And in fact, the script we saw, it has this glow, right? So yeah, this 800 MB file is essentially these learned W vectors. Okay, it's 100 dimensional per word. Okay, and you can look at the goodness of these words. So this is again like trying to debug CNNs. It's a way to debug. Okay, I created some task, learned something. Are the words, are there vectors even like are they even capturing anything semantic? You may be suspicious they may not be capturing anything semantically meaningful. So you can try to understand, what's going on. And one way, which we also saw for CNNs debugging, is you can always project these vectors into low dimensions and see what's happening with these words. Okay, project these things into low dimensions. There'll be 2-dimensional vectors or 3-dimensional vectors, and then instead of looking at that point, drop the word on top of it. Similarly to CNN case, where we had vectors for the images, and we dropped the images to these vectors to 2 dimensions, and instead of that point, we put an image there to see if similar images are clustered together. Okay, so here we'll try to see if semantically similar words are clustered together, and this is a very link a new tab maybe. Very crazy. The background is white, so you can't really see what's going on, but Yeah, so it looks like a mess, but you can try to see, for example, debt, price, stock, shares, are in the same area, business and management here. Here, local, foreign, national, public in the same space. So this is actually a projection, right? It may actually not give us the, it doesn't, we don't really know in high dimensions what's happening, but in low dimensions, we are trying to visualize whether they are semantically, whether they are close together or not, if they appear in similar contexts, okay? So that's one way. And it turns out that for this, the example that somehow someone created this task, it does have these clustering of similar words, okay? And the next few slides are just looking at, okay, what are the closest words to like things like countries' names or colors or technical words and so on. So you can look at these types of consequences later, but we just discussed this intuition. Okay. Yeah, so there are some details that I'm going to skip because I want to get to the specific details of Word2Vec, because then you'll understand exactly what was the task and what happened. So there are some consequences of once you created these embeddings, you can do this projection, the dimensional reduction, and see them. And there are also some nice consequences for, I don't know which embedding this was, but that's the link to the, I guess this is the link to the page that's talking about it. But it turns out that for certain type of embedding, they showed that the embedding of woman minus man, that vector, embedding is two vectors, right? Difference between two vectors is another vector, like a difference vector. So is the vector directionality is the same as the embedding of aunt minus uncle. Okay, these are just some curious consequences of these embeddings. They may not be true for your embedding and so on, but people have seen these types of consequences. And similarly, for example, France minus Paris plus Rome is equal to the country that Rome belongs to. I guess Rome is the capital. So Italy. Okay. So people have kind of tried to dig in, try to understand some embeddings. Okay. This is the understanding part if you have already trained embeddings. Okay. So so the next few slides are actually talking about uses of embeddings, but I think let's try to get to uses of embeddings. Actually, one of the uses was already we saw. We can actually use in the CNN sentence classification. Remember, there was a input matrix. So instead of that matrix, not instead of that matrix, in that matrix, each word should you can actually use this embedding vector. Okay, and that's precisely what's happening in that Python notebook. They're downloading the globe vector representations, and they're using that as the vectors to create that matrix for sentence classification. Okay. There are many other uses, but they're all, I think in the slides at least, we are being very superficial, very conceptual, so let's not spend time on that. I'll get to Word2Vec. Okay, so just to kind of ground how, I already grounded it with what the classification task was for in general case, but what happened with Word2Vec. Okay, that's going. Let's think of it as a case study. So in this task, okay, so Word2Vec, okay, so Word2Vec has two variations, and we're going to study one of them, okay, and the other one is just very similar to this. The two versions are called continuous bag of words and skipgram, just so that we know the names. And what we're going to study today is the skipgram version. Okay, it's just an approach which corresponds to some embeddings. Okay, so what do we need to specify? Okay, so what did Google do? So Google specified an auxiliary task. Okay, and the task is as follows. Okay, so you pick a word. So let's say you have a corpus. Corpus has a bunch of paragraphs, words, sentences, and so on. Pick a sentence. Okay. The idea is that, okay, I have a sentence or a collection of words similar to the previous example. I'm gonna pick a nearby word at random. Okay, so pick a word in the middle of a sentence. Doesn't have to be. Pick a word. Okay, it will be somewhere in the sentence. pick another word which is nearby to it, okay, which is close to it, okay, and make a network or make a prediction model learn learn in a way such that given the first picked word, it's gonna predict a high probability for the nearby word, okay. So let's actually ground it. So what is that task? The task is, let's say we have this sentence, the quick brown fox jumps over the lazy dog. Then I'm going to pick the word, so I'm going to create these pairs of words first of all. So let's say let me pick the word D, then the words near to it in that sentence are quick and brown, okay. And similarly, if the word is brown, then there are two words to the left of it, two words to the right of it, and which is what I'm calling as the nearby words, okay. So for example, for word brown, there are 4 nearby words, so I'll have 4 pairs of, four pairs here. These pairs are my training data, okay. So what is the task going to be? The task is going to be input the word which is the first word, which is the first word of the tuple, and I want to predict the second word of the tuple, okay. How do I predict the second word of the tuple? So let's assume I have vocabulary size of 10,000. Then my output, think of the output score vectors is a 10,000 dimensional vector, okay, which given this word, the word D as the input, is gonna, through the network or whatever, through the classifier, is gonna create 10,000 dimensional score vector, where the score for the quick word is the highest, right? The score for the quick word is the highest, okay. Similarly, pick any other word pair, fox and quick, for example. Again, fox is the input. Fox is the input. I mean, there's a vector corresponding to the word, that's the input. Remember, same embedding notion. And then goes to the classifier. And then again a 10,000 dimensional vector, where the output is hopefully high for quick and everything else low. Okay, so that's the idea. It's a different task than the task that I mentioned before. But this is the task that was chosen for the skipgram version of the Google's Word2Vec. Okay. So let's actually look at the diagram. So think of in this example, actually, they're exactly, 10, looks like the vocabulary size is 10,000. So let's say I have 10,000 words in my vocabulary. So in this case, let's say the word pair is fox and quick. Then the word corresponding to fox, okay, the word fox and quick is the current example. So I'm going to pick the row corresponding to the fox entry. Okay, wherever which row corresponds to the fox entry, that's the word, that's the weight vector that I need to pick up, right? That's the word vector that I need to pick up. Okay, that operation. Okay, so if it's let's say there's a 1-hot encoding of the vector 10 to the power 5 cross 1. Let's say this is the corresponding to fox. Let's say I have a W matrix, which is again 10,000 and 300 columns. Okay. Now, if it's fox, then I need to pick the corresponding row in the weight matrix. But that's essentially the same as saying I want to do. So let's call this vector V. This is the same as saying doing V transpose W. Okay. Yeah. So if I do V transpose W, I'll actually just pick that entry of that matrix which corresponds to fox. Okay. This is just a way to say, if you want to do lookup tables as a matrix multiplication, you can think of the vectors multiplying as these 1-hot vectors, and the matrix as a matrix, and then essentially like dictionary lookup is essentially the same as matrix multiplication. That's all. So their particular particular classifier that these guys use, Google, for the skipgram model is exactly given in this diagram. Basically, you have this 1-hot vector, okay, which is on the left side. Okay. And the edges here, these blue edges, correspond to that W embedding matrix. because the moment I pick one entry is essentially saying I have the one entry of my W matrix being selected. Okay, and that is that entry, one row is 300 dimensional. So think of that as my pre-activation, right? So I multiplied a vector with a matrix, I got an output. Think of that as a pre-activation. Remember, neural networks, I mean, we are basically doing w times x. Here I just flipped the x to the left side, but it's the same. I get a 300 dimensional vector. Now let's assume that the nonlinearity is identity function. Okay, no nonlinearity. Okay, I have a 300 dimensional vector. Now I'm just going to make it 10,000 dimensional because that's the dimensionality of my vocabulary size, by multiplying that 300 dimensional vector with another matrix, so that I get scores. Okay, I'm just increasing the dimensionality so I get scores. Once I get scores, I just do this softmax operation and get my cross entropy loss, right? That's it. So I'm just saying that their network is not really a deep network here. There's nothing complicated going on. The starting matrix is the embedding matrix. Pick the entry, that's my hidden vector. And from there, I'm going to a 1000 dimensional score vector such that I predict, if it's Fox, I have to predict quick, rather than if it's Fox and I have to predict something else. Okay, so the score corresponding to quick should be high. That's the goal. And what's the intuition? So why this looks like, okay, it looks like a very it's not clear why this network would give me a good embedding. The answer is, we know that for Fox we want to make quick the score corresponding to quick the highest, right? Now, if you want to make the score corresponding to quick the highest, then there's a linear transformation going on from the hidden this 300 dimensional vector to the score of quick. Let's say, I mean, in this case, I mean, it's able, but let's say this cell corresponds to quick. Okay, this vector corresponds to the word Fox. There's a linear transformation going from here to the word quick. You want the score for quick to be high, then it better be that the vector corresponding to Fox be high. Okay, of course you can also make the weights in this weight matrix high, but the weight matrix is common for all the data, right? For not just Fox and quick, it's also true it's the same weight matrix for some other pair of words as well. Okay, so if you think of this weight matrix as fixed, if the score for quick has to be high, then the vector corresponding to the corresponding word Fox in the training document also has to be high. That's all. It's all I'm trying to reason about is that when would you increase the score of your target, which is quick word, to be high? It has to be when the vector for the corresponding word in my training data set has to be not high, but like close to quick. Sorry. Right, we wanna create vectors where words which are appearing close to each other are similar, right? So if Fox is close to quick, and quick also has to be close to Fox, right? It's symmetric. I mean, so all I'm saying is, think of the second matrix as frozen. This thing which I'm showing here. If the Fox vector is here, then the quick has to be highest. If the quick vector is here, then the Fox has to be highest, some other coordinate, right? The only way those two that can happen is if the vectors of the Fox and quick are close to each other. Okay, so the objective function is fine. So here, I mean, so let me. I think I have an example with cat in the. This is fine. Okay. Yeah. So I guess this is the main slide. Remaining slides are just going into details of what I just described. So basically, words that are likely to appear around them. So think of words like fox. So in that sentence, the quick, brown, fox. So brown and fox appear close to quick, right? So brown and fox both are trying to predict quick. There are two examples in my training data where there's brown and quick, and there's fox and quick, right? So if they're predicting the same probability score, which is this high score for quick and everything else pretty close to 0, then their vector should be close because of this linear transformation. That's all I want to kind of say. Because the model is such that there is nothing going on in terms of nonlinearity and so on. If the vectors, score vectors are similar, then the input vectors have to be similar, right? I mean, that's kind of intuitive for a linear transformation. So that's all. So where is that sentence? Actually, let's just, yeah. So fox and quick, fox and brown. Okay, so fox and quick, and then brown and quick. Let's take these two examples. Brown and quick and fox and quick. First example in the last part, and second example here. So those two have to kind of predict the same score for quick. I mean, not the same score, but high score for quick and everything else 0. So I'm just saying that the vectors for brown and fox in this example has to be similar to each other, and only because they are appearing in a similar context. You may say, okay, brown and fox are semantically very different. Yes, but in this corpus, at least in this sentence, they are similar. Okay, that's all. So any questions about this part? I think I did this in a very long-winded way, but any questions? Okay, so yeah, so I don't think other details are needed. Yeah, so there's a couple of examples of how you would train a Word2Vec. How do you get these embeddings? So have a look at the examples. I think Facebook has some new embeddings, not really new, but 2 years ago maybe, called fast text. Essentially the same thing. In fact, fast text has embeddings for other languages, maybe even Hindi or Chinese and so on, French. So I think yeah. So let me pause there because everybody seems pretty tired. So any questions about this part? So Word2Vec, at least the task was clear. We just create an auxiliary task, get the right vectors, and the intuition is we just described that similar words appearing in similar contexts has to have similar vectors, and our task was such that it was true. Okay? Our task in this case, the classification task of having a score which is high for quick, having a high score for the word which is close to this word, then it just naturally happens that words which are in similar contexts will have similar vectors. Okay. So any questions? I see some faces which want to ask questions. Yes.
So can we do the same with embedding in this context with the embedding that we did for the images?
Yeah.
Because fine tuning and extraction by features. Can we do the same for as well data sets and so on?
Okay, so the question is, can we use these embeddings in a similar way that we did for image embeddings? So we use image embeddings as feature, extracted features, right? And then we could use that in an SVM classifier. So in fact, we did use the word vectors as embeddings in the sentence classification task. We just used embeddings as the starting point, and then did a simple classification, like a very shallow network, right? Only one CNN layer and one fully connected layer, actually, if you look at the code, or just few multiples of them. So we did use the word embeddings as pre-trained, vectors or feature vectors for words. Okay, yeah. Any other question? Yeah.
So going to that example of the quick from box
Yeah.
sentence.
Yeah.
We are actually trying to find the relation between each word and each other word in the vocabulary.
Yeah. So we want to predict my input is D, I should predict quick and brown the highest, quick highest and brown the highest. If I think of two separate examples, the input is input is the D, for example, in the first example. So there will be a vector corresponding to D. That's the hidden layer essentially, because it's a dictionary lookup on this side. So given the vector 300-dimensional vector for D, it's getting linearly transformed to a 10,000 dimensional vector. And in that score, that's essentially a score vector where I want to ensure that the score for quick is the highest. Okay. So for the score for quick to be highest, either the input has to be D, or the input has to be brown, or the input has to be fox. You can just see which words are trying to predict quick, right? So for all these three words, the quick vector has, quick score has to be highest. So these words appear in a similar context. That's the hand wavy argument here.
Each of these words will have a 10 to the power 5 dimensional vector.
No, each of these words will have a 300 dimensional vector. See, I think if you pick a word, the vector corresponding to the word is just a 300 dimensional row. So if a word is fox, then there's a row corresponding to this. That essentially you just rotate it, and that's the 300 dimensional hidden I guess activations in that Word2Vec diagram in the structure. Okay, 300 dimensional vector. So our embedding is a collection of, if I have 10 to the power 5 words in my vocabulary, then our embedding is just a collection stacking of these 10 to the power 5 vectors. Each vector is of 300 dimensions. Okay, and I'm trying to make these 300 dimension vectors the fox and something else brown similar to each other, because they all want to predict quick. Okay, because quick is like some sort of there will be a score vector where quick entry is the highest and everything else is low. Then these are the three words which should predict that. Because of linear transformation, these three words are going to be similar to each other, and that's why their embeddings are close to embedded vectors are close to each other. Yeah.
Now we figured out the embeddings.
Yeah.
So instead of giving the words as input, we give these as input.
Yeah.
So can you tell me in use case like how this will help, or what will happen next?
Oh, this will straight away help you. So remember, think of bag of words representation, right? So if I had 10 to the power 5 words, or 10,000 words, a bag of word representation essentially corresponds to a vector for each word, which is of length 10 to the power 5, where only that entry, like the fox entry, will be 1, everything else will be 0. So if you think of bag of words representation, the distance between fox and car is exactly 2 units, because they differ in 2 coordinates. The difference between fox and dog is also 2, right? But you think that, okay, semantically fox and dog should be close to each other and not close to car. Okay, so these embedded vectors, which are only 300 dimensional, not 10 to the power 5, are going to capture that aspect. Okay, so if you just use, instead of bag of words, these embeddings, you will get a gain, and that's what we saw in that paper that I was illustrating. You saw this, right? So where was this?
So instead of using like some PF ideas kind of transformations.
Yeah. So here itself you can see like bag of words SVM, and then word vectors SVM. I mean, for the first one you don't see much improvement, but I think the second corpus you see a huge improvement, right? So you see improvements across the board. I guess maybe not for this one, not, but you see improvements in general the moment you replace bag of words with word vectors. And if you use both, they're claiming that you can get maybe even a little bit more improvement, but yeah. So the use of embeddings is the same as using pre-trained networks in with vision. Yeah.
If I'm getting just an improvement of 3 or 4%,
Yeah.
I like put in so much effort to build this and to go with this improvement.
Good question. So I mean, so here you're not going to build this. I mean, somebody else like Facebook or whatever, they've already created this pre-trained network. So you will not, pre-trained embeddings. You will use that to, so you may be in your domain, you may not be having lots of data. So you'll never, you may want to capitalize on the English language, somebody else training other things on English language, and these word embeddings are an example of that. So somebody else maybe have trained on Wikipedia's data set, hundreds of gigabytes, got these embeddings, then that really do capture semantic meaning, and so you can just straight away use them for your domain where you don't have data. Okay, but if you're saying the improvement is small compared to bag of words versus this, that could be true. That could be true in some domains, but it does give you a bang per buck, and maybe that 2-3% is useful for you. It depends on the application. If you think it's too complicated, adds to complexity in your workflow, then and it's 2% is not worth it, then definitely not. Don't go for this. Yeah. Any other question? Yeah.
Can we get an extension for this assignment? If there are 2 exams and we have an exam on Saturday and get presentation on Monday, just a 2-day extension, maybe we can just.
Oh, if okay, so if your team wants a 2-day extension, just let me know. Yeah.
No, not one specific team, but
Really, everybody wants an extension? Because some people may not want an extension, right? Okay, so when the submission was on Tuesday night. Okay, submitted on Thursday night, maybe. Okay, that's it.